All right, everybody's awake, huh? Good morning, everybody. That's right. I see David's hands up. That's great. It's I know it's a fun week, and but we still have a lot of events, and it's my great pleasure to introduce our faculty candidate today, Dr. Wenli B from the University of Alabama at Birmingham. So. Um, the committee has been very impressed with Dr. B's CV. So she received her PhD from Washington University by 2011. And then she moved to APS, Oregon National Laboratory, for nearly 8 years each, from 2011 to 2019, initially as a postdoc, and then became a spectroscopist, and then became a senior spectroscopist because they have a lot of facilities. So then she decided to turn to join the academy at the University of Alabama, Birmingham, by 2019. And so she got actually tenured last year. That's the earliest whatever tenure I ever read among the people I have known. So before her tenure, actually, in 3 or 4 years window, she got 3 NSF awards, including 1 early career and 1 MRS and another regular one. So also she is a senior participant in one of the bigger grants received from DOE about the high pressure studies, including that part. So that's her expertise. Basically, over all of these years, she has developed a unique expertise, which is namely about high pressure study. So in addition to collaborate with physicists, chemists, right, and they have a strong overlap with geologists, all right, because a lot of times under high pressure, and the phenomena could be something useful for another set of expertise in our natural science. So she's an extremely productive individual. In addition to the success to the attracting external fundings, she obviously has a great record in her publication, otherwise cannot be going to a next step. So over years, she has published a bunch of papers. By now it's about 80 publications. Just by after moving to Alabama, she has literally published about 40 papers. So today she's going to introduce us her expertise about materials research under high pressure. Thank you.
Thank you, Rongying. Thank you for the invitation to be here. I was very flattered about the introduction. I don't feel like Rongying was talking about me. Again, my name is Wenli B. I'm with University of Alabama at Birmingham for over 5 years. This is first semester, my 6th year. As Rongying mentioned, my research is focused on understanding the material properties under high pressure. So we utilize quite a wide variety of techniques, and I'm going to show you later on some details. Rongying also mentioned our research is funded by National Science Foundation, and recently my group is also part of an ASA center funded by DOE, focused on understanding the complex materials, mostly additive manufactured materials under extreme conditions. So other than the in-house experimental research, we also use synchrotron facilities heavily. So here is a picture of advanced photon cells located inside Argonne National Lab. And in the last year, about a year or so, APS was shut down for upgrade after about 30 years of operation. So we've been also using advanced light source, AOS, at the Berkeley National Lab. Okay, as I mentioned, my research theme is experimental material research under high pressure. So we primarily focus on magnetism, try to understand the pressure tuning of magnetism and superconductivity. Very often you could induce superconductivity in materials that are not superconducting at ambient pressure, or you can actually change the Cooper pairing and manipulate the superconducting state. I'm going to show you one example later on. And of course, when you apply pressure to certain materials, you actually bring the atoms closer, so you can change the crystal structures routinely in a controlled manner. And also we study lattice dynamics, mostly using Raman or using inelastic X-ray scattering. And also we are interested in electronic structure because the crystal lattice is basically the host, and then when that's changed under pressure, and then the electronic structure can also be very often manipulated. So as I mentioned briefly earlier, experimental, we use a wide range of experimental techniques. For generating high pressure, we typically use a device called the diamond amule cell. So here is a sketch of a diamond amule cell, and I'm going to show you a little bit in more detail. And so we also, other than this diamond amule cell, we use a piston cylinder cell to generate hydrostatic pressure. And also recently we started to learn how to use a uniaxial electric piezo-driven uniaxial cell to introduce a directional tuning. Yes?
Oh, that is my question. So the piezoelectric, that's adding to the strain, or is you using it as a sensor?
Introduce strain on the material. Yeah. So this type of strain cell can be integrated inside a cryostat, or can be even used at a synchrotron beam lens. You see here is a transmission mode with windows, so you can have the X-ray going through and measure magnetic scattering or diffraction or other type of X-ray based experiments. So inside or in the high pressure condition, we also do different types of measurements. So for example, electrical transport. This is one example of having the probes fabricated onto the diamond amule cell tip. And another way is you just lay out the electrodes manually on the diamond amule cell, and you can have 4 probe measurements on the transport properties. And we also have this, we fabricate our own coils, miniature coils in the lab, and we can do magnetization, AC susceptibility measurements. And also, I'm going to show you later, we also have hydrostatic cell that can go into the quantum design PPMS with the VSM option, so we can measure magnetization under pressure. And we also combine with different type of synchrotron X-ray experiments. So here is a picture of X-ray diffraction. We can do single crystal or powder X-ray diffraction. We can also measure inelastic X-ray scattering to study the lattice dynamics, and other type of spectroscopy experiment combined with like a magnetic field or low temperature and high pressure conditions. And we also contribute to sample environment development at especially APS, collaborating with the magnetic material group and the inelastic nuclear scattering group. So we developed a different type of cryostats over the last several years to enable experiments like simultaneous sample environment of high pressure and low temperature. So this is different type generation of cryostat design that allow us to do different type of spectroscopic experiments and inelastic X-ray under high pressure and combined high pressure and low temperature conditions. Okay, so I mean, all this different type of experimental work were mostly carried out by my group. I currently have 3 graduate students, and a visiting professor just actually ended the visit from Tennessee, a liberal arts university, and 3 female undergrad students. And this summer, we just graduated 2 undergrad, and Trenton Culverhouse actually was awardee of the National Science Foundation Graduate Student Fellowship. Now he's a PhD student in physics at Cornell, and Bennett just moved to Michigan State University for the PhD program. Okay, so here is the outline of this talk. So I hope to give you some introduction about the pressure effect and how we actually generate high pressure. And as I mentioned, we use different type of synchrotron X-ray techniques combined with high pressure environment. So I hope to give you just a brief introduction on 1 or 2 techniques. Because this talk we use a lot of techniques. So if you have any question about anything I didn't make clear, just please ask me. I don't want to turn this talk into a technical talk. And then I'm going to give you case studies on 3 types of materials here. And then I will end the talk with a brief outlook. All right, so pressure, I think we, as a physicist, we are all physicists in this room, and we all know what is pressure. And pressure is really a very important thermodynamic parameter. It goes into the ideal gas law, and we are all also living in a pressure environment. I mean, without realizing it. I don't know how many of you actually appreciate or unappreciate how much is 1 bar of pressure. And so this 1 bar pressure is actually coming from the many hundreds of miles of air or atmosphere mass divided by a unit area, right? So this mass here, I don't know, you can read it from the back, low resolution, is 10 to the 3, so it's 1,000. If you count all the air molecule, if you make a column like 1 meter by 1 meter, and that amount of gas is actually 1,000 kilogram. That's a lot, right? But we are used to it, and then we don't actually feel this 1 bar of pressure. And then if you go up with high pressure, that this is the pressure range you can find on the Earth. And so we know our tire pressure is like 2 bars, a little over 2 bars. And we find the gas cylinders around the typical like 100 bar we use in the lab. And if you dive deep in the under the sea level, like the deepest sea level is the Mariana Trench near Philippines. That's about 11 kilometers below the sea level, and that pressure is roughly 1 kilobar. And if you go up with pressure in some way, if you can achieve around 1 GPa, which is 10 kilobar, and that's equivalently energy density of 6.2 billion electron volt per angstrom cube. And around this pressure, the most resilient creature, the tardigrade, the survival rate actually start to decrease. So lower than that pressure, you can't even kill the tardigrade. Of course, tardigrade is very difficult, very tough, right? Very difficult to kill. And if you turn up the pressure around 10 GPa also, actually 12 GPa, you can turn a very common semiconductor, gallium arsenide, into a piece of metal. And around 45, 50 GPa, that's the equivalent pressure you find in the Mars core. And around 100 GPa, if you manage to load oxygen into a pressure device and compress to this pressure, you cool down, and then you can actually turn oxygen into a piece of superconductor. So that's pretty amazing considering the large energy density you can achieve. And in this simple device, diamond amide cell, you can typically achieve a pressure as high as like 400 GPa or 500 GPa. And that's roughly the pressure you find in the Earth's core. So you can see here, this pressure actually has a pretty large energy scale and allow you to sample the different type of phases in a single material. Yes.
The diamond anvil, how high does it go? Where is it on this scale?
Okay, on this scale, there is a group from Germany actually claim they could achieve 1 terapascal, which is 1,000 GPa.
So beyond this.
Beyond this scale, yeah. Just to for a comparison, so roughly 100 Tesla, that's about 25 milli electron volt per angstrom cube, and 300 Kelvin, that's about 26 milli eV, and 100 GPa, that's equivalent to about 1,000 Tesla or 10 to the 4th of Kelvin. That give you some sense. Yes.
So how do you compare temperature with density of energy?
Well, if you convert the energy with the temperature, and so here is kind of equivalent to how bad or how much change on the volume. So when you change the temperature, I mean, this is just the equivalent. It's not a direct translation in energy. So 100 GPa is typical for around here. So like close to 1 electron volt per angstrom cube. So we are counting how much you reduce the volume and translate that into energy. Okay, here is another example. It's a lot of data, but you could just ignore these details. This is an example of pressure-induced insulator metal transition in this so-called quantum spin liquid material. I'm not going to go into detail about the physics of this material. Just want to show you at ambient pressure before compression, this material is actually insulator with indirect gap about 1.76 electron volt, and you compress on it, the color you can see becomes dark, and we all know the color is a reflection of the band gap, and so under pressure the band gap is closing, and what we found was there is a crystal structure transition with a very large volume collapse, and that's causing this closing of the indirect band gap. And with this finding is also confirmed with Raman scattering data. And just want to show you this pressure of 22 GPa also is sufficient to close a band gap of 1.7 electron volt. Another example is for the role to show the role of pressure in materials discovery is if you look at the history of superconducting critical temperature, and over the last slightly above 100 years, we have the conventional superconductors has pretty low TC, and in the 1980s, with the cuprate, initially this discovery of the different boost of the critical temperature was actually initiated by a high pressure study. When you squeeze on the material, for example, this lanthanum LBCO, and then the TC goes up, and that give us some insight. We need to substitute the material with a smaller ion, and then eventually lead to the discovery of the other type of cuprates with much higher TC. And that's also demonstrated recently with the big discovery of rare earth-based superhydride systems with a TC, a record high TC under very high pressure. And more recently, since starting from last year, there is also a report of superconductivity observed only under high pressure in the lanthanum, a nickel-based superconductor with a TC around 77 Kelvin or 80 Kelvin, above 14 GPa. Okay, so I mentioned to you we use diamond cell to generate high pressure and also other type of devices to generate high pressure in the lab. And basically, the trick is either you increase the load or you minimize or make the contact area smaller to achieve very high pressure. Okay, so the basic components here are two opposing angles, and you also don't want to have the two angles crushing on each other, and so you have typically a metallic gasket with high strength going between the two diamonds and form a sample chamber. So you load a piece of sample, and also you need to know how much the pressure is in the sample chamber. So we actually load a tiny piece of ruby on the scale 5 micron to 10 micron level. And very often we want to have as much of hydrostatic sample environment, so we put a gas pressure medium or liquid, or sometimes can be even solid like sodium chloride, soft pressure medium to have a quasi-hydrostatic environment. And we have, this is a picture of a small part of the collection of diamond cell in my lab. Just depends on what type of experiment we do. Either in a high magnetic field environment, so we use this cells made of copper beryllium. And if we do like single crystal X-ray diffraction, we use this other type of cells with large aperture to assess the higher 2 theta angles. And also this is called panoramic cell. We can allow the signal to be measured in the fluorescence geometry. We can take inelastic X-ray data. Okay, so the way we use Ruby to determine the pressure, so here is a loading of a real loading with a piece of sample and a tiny Ruby sphere. And when you shine the laser of certain wavelengths, green or blue, you can actually excite fluorescence from the ruby. Ruby is basically chromium-doped aluminum oxide, and there are two characteristic fluorescence lines, and we just keep track of the wavelengths. These wavelengths are already well calibrated against other type of standards, so we can read out the pressure directly and learn about the pressure scale on the sample. And so the setup is a very simple optical setup that can measure this type of fluorescence.
So the Ruby spectrum is calibrated to the pressure?
Yes. So it's typically done at a synchrotron. You know the equation of state of a certain calibrant, for example, copper platinum, silver, or gold. Or even very often we have neon pressure medium in here, and neon becomes solid about 5 GPa. And based on the equation of state of neon, we can learn about what's the sample pressure in there. Yeah. Okay, so I talk about the approaches to achieve high pressure, and we also need to be able to measure the property in situ, because you have seen the scale, the size of the sample is typically pretty small. It's on the level of 100 micron, even smaller. So it's extremely challenging to probe the sample property under this very constrained environment. So what we've been doing is we have this probes laid out on top of a gasket. So this is actually a rhenium gasket, and we have insulation layer on top of the metallic gasket, and we have the probes laid out, and we load a piece of sample on there. And we also have ruby. Of course, this was done in the lab, so we don't have access to synchrotron X-ray. And so the only way to measure pressure is through the ruby fluorescence. And we can also use different type of diamond annual cells. This type is just the screw driven, so you can just simply tightening the screws and apply pressure. And this is just another type that allow you to change the pressure in situ at any temperature and magnetic field. And this is some example to show the resistance measurement on the superconductor under different pressures and different magnetic field conditions. So you can learn about how the superconducting state is changing with pressure and magnetic field. Another technique we normally use in the diamond annual cell is this miniature coil for AC susceptibility measurements. And you can come up with different type of designs. For example, here people get a really creative and make a wedge shape instead of a cylindrical shape. And you can also deposit or grow this coil onto the diamond annual cullet, and you have a much enhanced filling factor in this case. And here you have a tiny sample but a big coil. And you can actually measure with this coil. You can measure, for example, superconductivity in lithium. This was done in Professor Schilling's lab several years ago, 20 years ago. And this beautiful data shows a clear superconducting transition under pressure. And you could also, if you manage to increase the filling factor, you can track of the magnetic ordering temperature under pressure and the type of magnetic order. As I mentioned, in the second slide, this is a hydrostatic piston cylinder cell that you can put in the PPMS VSM coil. If you have a large ball coil, you can actually measure magnetization up to 1.3 GPa. And in this case, the sample size is very decent and comparing to the sample size in the diamond annual cell. So you can actually study the superconductivity pretty easily. This is an example of palladium telluride under high pressure. And also, this is another type of piston cylinder cell that we can put oil pressure medium in there and seal it, and also achieve hydrostatic pressure medium up to 3 GPa. Okay, so another technique is we use commonly is a synchrotron-based X-ray. So the reason to use a synchrotron-based X-ray is the diamond, although it's optically transparent, it actually absorbs X-ray in a certain energy window heavily. For example, several kiloelectron volt after 2 millimeter of diamond, that's the typical thickness of diamond we use, almost nothing left. So like absorption is 99-point-something% for that energy. So the synchrotron X-ray is, in this case, advanced photon source is well known for hard X-ray applications. So the typical energy scale is higher on the level of tens of kiloelectron volt, and in that range is diamond absorption is almost negligible. You don't have to concern too much. And that's also a reason of synchrotron facilities like APS put a pretty large focus on high pressure research. In fact, there are at least 3 or 4 sectors. They dedicated some of the beamlines for high pressure research. So APS, this is just an overview. At APS, so it's a synchrotron is typically a big circle. So at APS, I mean, it's different from AOS or other synchrotrons. There's 35 sectors, and in total of about 50 beamlines. And each beamline, they have dedicated setup, X-ray setup for different type of techniques. For example, absorption, emission, diffraction, or other spectroscopy techniques, and also dedicated sample environment for like high pressure or high field or even time-resolved studies. And we've been using at least 6 beamlines frequently at APS. And if anyone is interested in different type of research capabilities, at a synchrotron X-ray facility combined with high pressure, this is a great overview paper. And if that apply to your research, I encourage to consider using APS. Before I go into the examples, the results what we've been published recently, I want to introduce very briefly Mossbar effect. So Mossbar effect is basically a recoilless absorption and emission. And it's first discovered by Mossbar in 1959, and 2 years later he was awarded a Nobel Prize. So this technique is, the physics is very, very simple. The recoilless means you don't consider your recoil during the absorption process. And just like a resonant acoustic resonant case, when you have like 2 forks and you have if you want to have a resonant case, you need to have the 2 energies of the wavelengths matching each other exactly. And the reason is in a solid, the typical recoil energy is on the level of milli-electron volt, but your energy resolution is on the level of nano-electron volt. So if you have a recoil correction term on the level of milli-electron volt, you won't be able to observe anything on the level of nano-electron volt. So it's fairly simple, and that's why it's called a recoilless emission and absorption technique. And so this technique has been pretty powerful and applied in many type of research. For example, it's also this miniature Mossbar spectrometer has been mounted on several Mars exploration rovers to study the iron-based minerals. Okay, this is a very busy slide, but I'm gonna just briefly mention the fundamental physics, how we actually apply the Mossbar effect in material research. So the type of interactions, basically 3 types of interactions here are relevant to understand the electronic structures and magnetism. So the first high-profile interaction is called the isomer shift. It basically measures the density of state at the nucleus level, because nucleus is not a point charge. It actually has a volume, and the isomer shift is just reflection of how much electron density at the nucleus location. And that's, of course, is dominated by s electrons. but of course the outer shell also has an impact to the x electrons. So you have, even you are measuring a simple parameter, it actually show up dramatically when you have a change in the electronic structure induced by pressure or induced by magnetic field or even temperature in some case. When you have, for example, valence state change, and then you have a dramatic change in the isomer shift. And
why is it called isomer shift? Is it like connected with number of, like the isotope, or?
Yes, it is. It is related to specific isotope. Yeah, I'll show you.
But why does it change the electronic structure?
Okay. Well, I mean, so this is most part, in fact, is isotope-based technique. So you are sensitive to the isotope you are probing, and the isomer shift. Well, I mean, it's basically you are measuring or you are sensing the isoelectron density, right? So you are imagine you are a nucleus. You are looking around in the eyes of a nucleus, and any electronic structure change would have an impact. So you can tell, you have a spin transition. You have a high spin, low spin going into high spin going to low spin. You can sense that, and you could also sense when you have some case you have electronic occupation change. You have oxidation state change, and that would also show up in this case because you have electronic redistribution or hybridization, and that also show up in the isomer shift.
Thank you.
Okay, the charge distribution of the nucleus will be different for different.
The charge distribution, yeah, of course, that's the source, yeah. So then you,
sensor to the profile.
yes. And also another parameter called quadruple splitting, and this terminology is specific to iron, but it basically can also tell the crystal structure transition when you have a different distribution, electric field gradient around the nucleus that also show up in this quadruple splitting parameter. And of course, when you have a hyperfine magnetic field around the nucleus, and that also show up in the nuclear Zeeman splitting. And then based on this different type of interactions, you can get a picture of what's going on with the electronic environment. Okay, I think many of you know this technique actually achieved in the lab using a radioactive active radioactive source. For example, for iron 57 isotope, you use a cobalt 57, and just using that radiation, decayed radiation, and you excite your iron 57 nucleus to the excited state, and you look at what's going on after the interaction. So at the synchrotron beamline, you can actually get rid of the dirty radioactive parent source and just tune your X-ray energy at that nuclear resonant energy and take data in the time domain and look at how the decaying behavior in the different type of electronic conditions. And so this synchrotron, because synchrotron beam can be focused to a very, very small size, typically several microns, or even now after upgrade is a sub-micron size. And synchrotron is much, much brilliant, has higher brilliance than a typical lab X-ray source. So you can easily integrate it with a pressure or temperature or magnetic field environment and enable you to study the materials. So here is several basic parameters for iron 57 and also europium 151. And so this is the different resonant energy, the excitation energy, length, and lifetime, abundance. So europium is really favorable because this specific isotope is naturally very abundant. So we don't need to artificially enrich the sample. We just take a europium-containing compound and just take data directly. But a lot of the time using iron-57, you do need to consider artificially enrich the sample so you have a higher interaction. Okay, I'm gonna skip this. So this basically shows the transition scheme just based on the dipole selection rule. And in europium, in the case of europium-157, you have 18 transition lines. When you turn on the hyperfine magnetic field, and with the modeling, you can write down the Hamiltonian and then put it in the program. You can actually resolve all the, extract all the hyperfine parameters. Just a bit of a brief introduction on this compound. I think because Rongying I saw in the hallway, there are several posters about this material is quite important material for the recent topological magnets. There are several predictions claiming you could, by either introducing pressure or other chemical approach, you can, if you can turn the magnetic configuration from the in plane to out of plane ferromagnetic order, then you could have ideal potential, ideal well semi-metal. So you can turn this into a very ideal well state, and that's a big deal because there are many groups have been looking for this ideal well semi-metal candidate. So this is one of the motivation we try to apply pressure to manipulate the magnetic configuration, and hopefully we can confirm it go into this predicted well state. Another compound is also quite unique compound is the europium manganese antimony. Is supposed to be a direct semi-metal. In this case, you have europium and manganese, two different type of magnetic species, and there's a lot of rich physics about the correlations of the interactions between the two species, and also the crystal structure, and in this case is quite unique. And also it has been predicted under high magnetic field, also confirmed experimentally. If you apply magnetic field along the different crystal axes, you can actually easily tune this into different type of topological and different you can actually control the band gap easily. For example, here you can easily close this band gap by applying magnetic field with the field direction along BC axis. So this is the basic motivation. We want to use high pressure instead of very high magnetic field, and to check whether indeed we can control we can drive these systems into predicted ideal state. Okay, take this compound as an example. So we first confirmed this. The compound start with antiferro, a type A antiferro magnetic state with the ordering temperature under 10 Kelvin, and we applied the pressure and to look at how the crystal structure is changing, because the earlier prediction is on the basis of the crystal structure need to be conserved, and so that's the symmetry need to be conserved first, and then also the europium valence state need to be maintained, because europium is a special element in the periodic table along the lanthanides is a mid member, and in this case, europium is a 2+, has 7 foil electrons. However, if you are familiar with the lanthanide contraction under pressure or temperature or magnetic field, you can easily control the valence state or the number of foil electrons, and then you can manipulate the magnetic order or the magnetic configuration in this case. Yes.
Can you sort of remind us what is a wild semi-metal?
The wild semi-metal, okay, so back to this, is because this spin orbit coupling, and then you have this band inversion and the near Fermi level. So in the ideal case, near the Fermi level, you have a linear dispersion, and that's so it show up in as a pair. You have the different chirality, and in this case, if you have ideal well semi-metal, then your this ideal this well nodes well points appear at the Fermi level. So, because the magnetism on europium is closely related to the crystal, to the valence state of europium, how many foil electrons in there, and also the symmetry crystal structure is critical to achieve the predicted topological state. So we first look at how the crystal lattice is changing under high pressure. We took X-ray diffraction data and keep track of the crystal possible, or look for possible crystal structure transition, and we found even to 34 GPa, the trigonal crystal lattice is still maintained. And although when we plot the C/A ratio, the axial ratio and the volume, we clearly see an anomaly in the C/A. However, we don't see anything in the volume, the equation of state. So here, C/A typically suggests some sort of electronics transition there. And then we we said, okay, it's great, the crystal symmetry is maintained, and how about the magnetism? Is really the magnetic configuration is tuned into a outer plane ferromagnetism, and so we took the sample in the dynamic cell to the synchrotron beam and used the synchrotron-based Mossbauer spectroscopy in the europium 151, and then we look at the forward Mossbauer scattering signal, and in this case, you see here you have the whole bunch of oscillations, and by modeling these oscillations, you can get a sense of the, let's say, the electric field gradient, the quadrupole splitting, and also the hyperfine magnetic field. And the hyperfine magnetic field reflect the strength of the interaction, the magnetic ions, and also when you have a spectrum like this, when there is no quantum oscillations, you know that this europium ions is in the paramagnetic state. So this basically tell you a lot of information about the again, the electronic environment and also the magnetic ordering temperature. So from this data set, we got a magnetic ordering temperature shooting up to almost 90 something Kelvin from about 10 Kelvin at a pressure of 43 GPa. And we also didn't see the change of magnetic configuration going out of plane. This technique, if you use a single crystal, you can actually resolve the angle of the X-ray propagation direction with the crystal lattice plane. So what we found was the sample remains in the magnetic configuration remains in plane rather than out of plane. So, I guess this experiment confirmed this compound did not go into the ideal well state as predicted. Okay, yes, I should have gone a little faster. I'm gonna just show you another example of X-ray technique. Is the so-called X-ray absorption can actually directly probe the valence state or oxidation state of a certain ions. So this technique is element selective rather than the Mossbauer effect is isotope selective. And in this case, you can actually sense the electronic, probe the electronic transitions, electronic environment more directly. So we intentionally choose L3 edge that can probe the 4F electron occupation more directly. And we confirmed that the European valence state remains divalent rather than potentially under hypertion, which was observed in many compounds, can easily go into a 3+ state. So that's good. And the unfortunate thing, we didn't see the magnetization is driven into the outer plane state. Okay, I'm gonna skip this. This is just a comparison with different compounds. We see all kinds of behaviors, and that's very specific to the detailed electronic structure of even it's kind of a similar crystal structure, crystal symmetry, but it's a very different electronic structure. Okay, so in this compound here, as I introduced earlier, what we found was under high pressure, the magnetic ordering temperature goes up to also almost 10 factors, tenfolds. It started like 20-something Kelvin and goes almost above 180 Kelvin with only 28 GPa. And we also found through X-ray absorption at the European L3 edge and the manganese K edge, we found that there is significant hybridization of European 5D electrons with the manganese 3D orbitals, and that could be the reason the enhanced magnetic ordering temperature. Okay. Due to the limited time, I think I'm gonna just skip this iron tin Kagome magnet. So in this system, we found two crystal structure transitions, and that's associated with the suppression of magnetic order. And I just want to mention one thing. In this case, it's this Kagome lattice is basically a special arrangement of atoms, and because the electronic destructive interference, and you have a flat band near the Fermi level, and in this specific case, we have actually two type of bondings between the ions, and these two bonds are just small, very slightly varied. So these two bonds just by less than 1% of difference in bond length, but we can actually sense that using the Mossbauer effect. You just need to assign these different hyperfine interactions, hyperfine magnetic field to different bond lengths, and we can sense very small variation coming from the iron-iron exchange interactions. Okay, the last example I want to give is the pressure-induced superconductivity in nickelates. As I mentioned earlier, the nickelates was this 327 compound was just discovered, reported last year to be superconducting around 80 Kelvin and only under high pressure. And so but there are a lot of open questions and also a lot of reports on controversial results. So we took one of these special phases, so-called the 2222, so the bilayer lanthanum 3, nickel 2, oxygen 7 phase, and we compress it and we look at how the crystal structure is changing, and we confirm there is a orthorhombic to tetragonal transition that's responsible for the pressure-induced superconductivity, and we also simultaneously detect the transport and to look at how the band gap is behaving and how we actually, whether we can drive this into a special phase, 2222, into a superconducting state. So indeed, we saw a sharp drop of resistance right above 15 GPa, as reported in the original Nature paper last year, and the critical temperature matches exactly as the reported 80 Kelvin. However, when you apply magnetic field, this onset temperature doesn't change at all, almost no change, although there is a broadening at the lower temperature, and that's suggests that the system is indeed and the shift to lower temperature. So indeed it is a superconducting, or could be a filamentary superconductivity, but there is also many open questions whether this is a pure superconducting phase. Doesn't look like, because first of all, resistance doesn't go to 0, and second of all, the onset temperature doesn't shift with applied magnetic field. So we plan to follow up this study and expand it to other type of rare earth based nickelate systems. And right now we are measuring some other nickelate compounds with some doping like neodymium or samarium, praseodymium, and also we are trying to stabilize the superconducting phase, hopefully with other doping like cobalt replacing nickel or copper. And we also would like to know what exactly going on in the phase right before the superconducting phase using synchrotron radiation. Okay, if I can have 2 more minutes. So this is some, again, future work on pressure tuning of quantum magnets. So we plan to study a binary European-based systems, and hopefully we can have a clear idea on the strong correlations and how that impact on the topological phases. And this is just some preliminary calculations and observation of CDW in a European bismuth compound. And also we are interested in a systematic study of this 111 systems combining with chemical approach and also external pressure. And this is another example on frustrated magnets. We have the a square lattice system, and using pressure we can control the competing exchange interaction and access the different type of phases. Okay, with that, I'd like to acknowledge the collaborators, including Rongying here, and I'll be happy to take any questions. Thank you very much. Open for discussion. Yeah.
So I wanted to ask about the nickelates. So unless somebody invents an explanation, your results basically show that they're not superconducting.
Our results show that it's an open question, I would say. So first of all, this sharp drop, I mean, we didn't see it go into, we didn't see the zero resistance. So zero resistance is a confirmation, right? Whether you have a true superconductivity. However, in this case, there is some argument about, this phase could start with a 1-3-1-3 instead of a pure bilayer. People have done TM to show that. And in our case, we intentionally started with a 2-2-2-2 phase, which is supposed to be the superconducting phase. And still we see the resistance didn't go to zero. And also the question, I think the critical question is why that onset temperature didn't shift at all. And so, sorry.
It's actually very common for the onset temperature to not shift. Even in cube rates, in many situations, you have only broadening.
Yeah.
And actually only a detailed analysis of that curve can give you an idea whether it's due to flux motion in the superconductor.
Yes.
This thing here is not
Yeah.
balanced.
Also, yeah. So you mentioned that we have this rising tail that we couldn't understand. So my theory was this is a filamentary, and there is a competing phase that causing this rise of resistance, because before that we also have a semiconducting state, and then we just turn there's a semiconductor to metal transition, but you see here, especially in this curve, there is a sharp rise after a so-called, it could be a SEW phase, and I think there could be some competition of superconducting phase and non-superconducting phase. Whatever that non-superconducting phase is also very critical.
Yeah, in that little thing has been really heavily debated in the last few years. Even a couple of Nature papers have been generated.
I think also, if you just have junctions and a quasi-particle tunneling, that can give an upturn at low temperature.
Right.
As I said, it's low dimensional and it could be multi-phase. Different
You have a
regions
question,
behave
Max?
differently.
Actually, I was kind of curious about that. When you measure your conductivity at high pressure, you also pressurize your copper leads, right?
Yes.
So are there any, how do you separate the effects on sample from your substrate effects?
My substrate.
Well, the copper, right? I mean,
The
you also
wires.
So,
wires.
right.
So
In other words, could the copper be superconducting under pressure, for example? That's my translation.
Yeah, we normally use platinum. Platinum is not a superconductor under very high pressure. People have done that, yeah. And so these probes, the material of the probes are carefully chosen. And even I showed earlier, you could deposit fabricate the probes on the diamond cell on the tip, and very often we use tungsten. And tungsten doesn't superconduct under very high pressure also.
Okay, thank you.
All right, Mas.
Can you, so obviously this is very good technique to apply pressure to single crystals that
Yeah.
have been lab grown. Can you talk, you mentioned a number of ways to apply pressure.
Yeah.
What other kinds of sample geometries? Are you stuck with single crystals, or can you look at films on substrates? Can you look at composite materials? What kinds of, can you comment a little on how to broaden
Yes.
the applicability?
Yeah, so first of all, it depends on the pressure range you want to go to. And for low pressure, several GPa, the envelope can be, the tip of the envelope can be big, and your sample can be as big as, 200 micron, 300 micron. If you want to have hydrostatic environment, you put your sample in the liquid before the freezing pressure and before it turns into solid, and then you have pure hydrostatic environment, and then you could do all kinds of measurements. And about the thin film or bulk, it depends on the detection method. And if you want to do X-ray, depends on the X-ray technique and the energy you want to use. Maybe could be limited in some case. If you have a very thin layer of sample, and your interaction path is too small. Very often we do like a trick, grazing incidence, and in the dynamic cell, again, the opening is limited and it can be challenging. But if you do like transport measurements, there is still ways to attach the probe on the thin film.
Yeah, I guess I was thinking transport, and also you showed these ultra small AC susceptibility coils.
Yeah, yeah. Then in that case, you just you don't need to introduce any probes inside the sample chamber, and you could measure Meissner effect or the change of susceptibility from magnetic order.
So the
Yeah.
Mossbaum effect is only applicable to iron and europium?
Okay, yeah, that's a great question. In fact, at APS, at the Advanced Photon Source, they routinely do 5 isotopes. So iron 57, europium 151, dysprosium 161, and tin 119, and krypton, I can't remember because I never use it because it's very rare. Yeah.
So only material that contain these
Yeah.
elements you can use this effect to probe.
To probe the.
Otherwise, you will have to use other.
Yeah, other techniques. For example, you could, if you're interested in magnetism, you could do like XMCD. It's just the X-ray magnetic circular dichroism. Or you could do magnetic scattering. Yeah.
All right, it's getting late. Thank you all. Thank you, everyone. One more time.
Thank you.